Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. This is a podcast where I read old books, sometimes fiction, sometimes non-fiction, in the most boring way I can, to try and help slow your spinning mind enough for you to fall asleep in the most natural way possible. The stresses of life often follow us to bed and keep us company, but I'm here to distract you from them and help you to drift away. But before you do fall asleep, if you find Sleepy Time Tales helpful and you would like to support me to help me keep it going out to you and thousands of your fellow insomniacs, please consider supporting on the Patreon at patreon.com/sleepytimetales. If monthly is a bit much, you can also put a tip in the tip jar. Both of these options are linked in the show notes. And you can also support Sleepy Time Tales by simply spreading the word. If you know someone who's struggling to sleep, tell them about it and tell them where to find it. And that's enough of that. Let's get on with learning about the moon. So snuggle down, close your eyes, breathe deeply, and listen closely as I lead you down the path to sleep. This week we return to Astronomy, the Science of the Heavenly Bodies, by David P. Todd. Chapter 28. The Moon and Her Surface. As the sun has always reigned as king of day, so is the moon queen of night. Observation of her phases, now waxing, now waning, with her stately motion always eastward among the stars, began with the earliest ages. Often when near the full she must have seen herself eclipsed, and much more rarely, the occurrence of total eclipses of the sun is certain to have suggested the moon's intervention between Earth and sun, shutting off the sunlight completely, because these eclipses never took place except when the moon was in the same part of the sky with the sun. If we watch the nightly march of the moon, we shall find that she travels over her own breadth in about an hour's time. By using a telescope on the stars just eastward or to the left of her, she will now and then be seen to pass between us and a star, on very rare occasions a planet, extinguishing its light with great suddenness, the most nearly instantaneous of all phenomena in nature. Draw a line connecting the cusps or horns of the lunar crescent, and then a line eastward at right angles to this, and it will show the direction of the moon's own motion in its orbit round the Earth quite accurately. As the phase advances, note the inside edge of the advancing crescent. This will be quite rough and jagged compared to the outside edge, which is the moon's real contour, and relatively very smooth. The position of the inside curve will change from night to night, and it marks the line of sunrise on the moon during the fortnight elapsing between the new moon and full. While from the full through last quarter and back to new moon, this advancing line marks the region of sunset on the moon. The general shape of this line is never a circle, but always elliptical, and astronomers call it the terminator. All along the terminator, sunlight strikes the lunar surface at a small angle, whether near sunrise or sunset, so that owing to the mountains and other high masses of the moon's surface, the terminator is always a more or less jagged and irregular line. Onward from new moon toward the full horns of the crescent are always turned upward or eastward. When the general line of the terminator becomes a straight line from cusp to cusp, the moon is said to have reached first quarter or quadrature. Onward toward full, the terminator will be seen to bend the other way, and in about a week's time it will have merged itself with the moon's limb. The moon then is said to be full. Afterward, the phase phenomena recur in the reverse order, with the third quarter midway between full and new moon again, the phase of the moon being called gibbous, all the way from the first quarter to third quarter, except when exactly full. As we know that the moon is, like the Earth, a non-luminous body, and shines only by virtue of the sunlight falling upon it, Clearly an entire half of the moon's globe must be perpetually illuminated by sunlight. The varying phases then are due simply to that part of the illuminated hemisphere which is turned towards us. New moon is entirely invisible because the sunward hemisphere is turned wholly away from us, while at full moon we see the lunar disk complete because we are on the same side of the moon that the sun is, and practically in line with both sun and moon. If we could visit the moon, we should see the Earth in exactly complementary phase. At new moon here, we would be enjoying full Earth there. And full moon here would be coincident with new or dark Earth there. The narrow crescent of new moon here would be the period of gibbous Earth there. And it is the reflection of sunlight from this gibbous Earth which illuminates the part of the moon, but faintly seen at this time, popularly known as the old moon in the new moon's arms. Its greater visibility at some times than others is due to greater prevalence of clouded area in the reflecting regions of the Earth turned toward the moon, and the higher reflective power of clouds than that possessed by mere land and water. As the moon goes all the way around the sky every month, the same as the sun does in a year, and travels in nearly the same path, clearly it must also go north and south every month as the sun does. So in midsummer, when the sun runs high upon the meridian, we expect to find full moons running low, and likewise in midwinter the full moon always runs high, as almost everyone has sometimes or other noticed. This eastward or true orbital motion of the moon is responsible for another relation which soon comes to light when we begin to observe the moon, and that is the later hour of rising or setting each night. Our clock time is regulated by the sun, which also is moving eastward about 1 degree daily, or twice its own breadth. So the moon's eastward gain on the sun amounts to about 12 degrees daily, and 1 degree being equal to 4 minutes, the retarded time of moonrise or moonset each day amounts to very nearly 50 minutes on average, though sometimes the delay will be less than half an hour, and at other times it will exceed an hour and a quarter. The season of least retardation of rising of the full moon is the autumn, and so the moon that falls late September or October is known as the harvest moon, and the next succeeding full moon is called the hunter's moon. Lunation is a term sometimes given to the moon's period from any definite phase round to the same phase again. Its length is the true period of the moon's revolution once around the Earth, from the sun all the way around till it overtakes the sun again. The synodic period is another name for lunation, and its true length is 29 and 1/2 days, or very accurately, 29 days, 12 hours, 44 minutes, 2.7 seconds, as calculated by astronomers, with great exactness from many thousand revolutions of the moon. But if we want the true period of the moon round the Earth as referred to a star, it is much shorter than this, amounting to only 27 days and nearly 1/3. This is called the moon's sidereal period of revolution, because it is the time elapsed while she is traveling eastward from a given star, around to coincidence with the same star again. If we follow the moon's path in the sky more critically, we shall find that it does not quite follow the ecliptic, or the sun's path, but that twice each month she deviates from the ecliptic, once to the north and once to the south of it, by roughly 10 times her own breadth. More accurately, this angle is 5 degrees, 8 minutes, 40 seconds, an almost invariable quantity, and it is therefore known as an astronomical constant, or the inclination of the moon's orbit to the ecliptic. So the moon's orbit must intersect the ecliptic, as both are great circles in the sky. The points of intersection are known as the moon's nodes, one ascending and the other descending, and the nodes are 180 degrees apart. The figure of the moon's orbit is not circular, although it deviates only slightly from that form. But like the paths of all other satellites around their primary planets, and of the planets themselves round the Sun, the moon's orbit is also an ellipse. The distance of the moon's center from the Earth's center is therefore perpetually changing. The point of nearest approach is called perigee, and that of furthest recession, apogee. The moon's distance from the Earth is easier and simpler to be ascertained than of any other heavenly body, because it is the nearest. An outline of the method of finding this distance is not difficult to present, and it resembles in every particular the method a surveyor uses to find the distance of some inaccessible point, which he cannot measure directly. Up and down a stream, for example, he measures the length of a line, and from each end of it he measures the angle between the other end of the line and the object on the opposite side of the stream whose distance he wishes to find out. Then he applies the science of trigonometry to these three measures, two of angles and one the length of the side or base included between them, and a few minutes' calculation gives the distance of the inaccessible object from either end of the baseline. To transfer the process to the sky, let the two ends of the base be represented by two astronomical observatories, for example, Greenwich in the northern hemisphere and Cape Town in the southern. The baseline is the chord, or straight line through the Earth connecting the two observatories, and we know the length of this line pretty accurately because we know the size of the Earth. The angles measured are somewhat different from these in the terrestrial example, but the process amounts to the same thing, because the astronomers at the two observatories measure the angular distance of the center of the moon from the zenith, each using his own zenith at the same time, and the same science of trigonometry enables them to figure out the length of any side of the triangles involved. The side which belongs to both triangles is the distance from the center of the Earth to the center of the moon, and the average of many hundred measures of this gives 238,800 miles, or about 10 times the distance around the equator of the Earth. We've said that the orbit in which the moon travels around the Earth is practically a circle, but the Earth's center is found not at the center of this orbit, but set to one side, or eccentrically, so that the distance spanning the centers of the two bodies is sometimes as small as 221,610 miles at perigee and 252,970 miles at apogee. The moon's speed in this orbit averages rather more than half a mile every second of time, more accurately 3,350 feet a second, or 2,290 miles per hour. Once the Earth's distance is known, its size or diameter is easy to ascertain. An angular measure is necessary, of course, that of the angle which the disk of the moon fills as seen from the Earth. There are many types of astronomical instruments with which this angle can be measured, and its value is something more than half a degree, 31 minutes 7 seconds. The moon's actual diameter figures out from this 2,163 miles, and it would therefore require nearly 50 moons merged in one to make a ball the size of the Earth. Still, as no other planet has a satellite as large in proportion to its primary as the moon is in relation to the Earth. But the materials that compose the moon have less than 2/3 the average density of those that make up the Earth, so that 81 moons fused together would be necessary to equal the weight or mass of the Earth. If we figure out the force of attraction of the moon for bodies on its surface, we find it equals about 1/6 that of the Earth. Athletes could perform some astounding feats there, miracles of high jump and hammer throw. Our interest in the moon's physical characteristics never wanes. Her nearness to us has always fascinated astronomer and layman alike. Early users of the telescope were readily led into error regarding the general characteristics of the lunar surface. and it is easy to see why they thought the smooth, level plains must be seas, and give them names to that effect which persists to this day, as Mare Crisium, Mare Serenitatis, and so on. We may be sure that no water exists on the moon's surface, although some astronomers think that solid water, as ice or snow, may still exist there at a temperature too low for appreciable evaporation. Perhaps water, seas, and oceans were once there, but their secular dissemination and loss as vapor have gone on through the millions and millions of years, till even the moon's atmosphere appears to have vanished completely. At least there is much better evidence of absence of atmosphere on the moon than of its presence. Not enough at any rate to equal 1,000th part of the barometric pressure we have at the Earth's surface. Frequent observations of stars passing behind the moon in occultation have satisfied astronomers on this point. We often say of the brilliant full moon, it is bright as day. The photometer, or instrument for accurate comparison of lights, their amount and intensity, tells a different story. Indeed, if the entire dome of the sky were filled with full moons, we should be receiving only 1/8 of the light the sun gives us, and would require more than 600,000 average full moons to equal the light radiation of the sun. Heat from the moon, however, is quite different. Early attempts to measure it detected none at all, but with modern instruments there is little trouble in detecting heat from the moon, though measurement of it is not easy. Much of the moon's heat is sun heat, directly reflected from the moon, as sunlight is, but most of it is due to radiation of solar heat, previously absorbed by the materials of the lunar surface. The actual temperature of the moon's surface suffers great variation. The fortnight's perpetual shining of the sun upon the lunar rocks would certainly heat them above the temperature of boiling water. If the moon had an atmosphere to conserve and store this heat, but the entire absence of such an air blanket probably permits the sun's heat to be radiated away nearly as fast as it is received, leaving the temperature at the surface always very low. What physical influences the moon really has upon the Earth must be very slight, barring the tides. But there is little hope of getting people generally to take that view, because the moon appears to be the planet of the people, and the opinion that the moon controls the weather, for instance, amounts with them to practical certainty. More than likely, all these notions are but legitimate survivals of superstition and astrology. In addition to the tides, our magnetic observatories reveal slight disturbances, with the swinging of the moon from apogee to perigee and back. But long series of weather observations have been faithfully interrogated, with negative or contradictory results. If one believes that the moon's changes affect the weather, it is easy to remember coincidences, and pass over the many times when no change has taken place. The moon changes pretty frequently anyhow. As Young well puts it, a change of the moon necessarily occurs about once a week. All changes of the weather, for instance, must therefore occur within 3 3/4 days of a change of the moon, and 50% of them outright occur within 46 hours of a change, even if there were no causal connection whatever. When we turn to the strongly diversified surface of the moon itself, we find much to rivet the attention, even with slender optical aid. Everyone wants to know how near the telescope, the biggest possible telescope, brings the moon to us. That will depend on many things. First of all, on the magnifying power of the eyepiece employed on the telescope. And eyepieces are changed on telescopes just as they are on microscopes, though not for the same reasons. The theoretical limit of the power of a telescope is usually considered as 100 for each inch of diameter or aperture of the object glass. A 40-inch telescope, as that of the Yerkes Observatory, the largest refracting telescope in existence, should bear a magnifying power not to exceed 4,000. But this limit is practically never reached. 1/2 of it, or 50 to the inch of aperture being a good working limit of power, even under exceptional conditions of steadiness of atmosphere. If we reduce the effective distance of the Moon from 240,000 miles to 100 miles, that is about the utmost that can be expected. But even at that distance we can make out only landscape details, nothing whatever like buildings or the works of intelligence. The larger relations of light and shade, so obvious to the naked eye on the Moon, vanish on looking at it with the telescope. But we are at once captivated by the novel character of the surface and the seemingly great variety of detail that is clearly visible. As soon as the new moon comes out in the west, we may begin to gaze with interest and watch the terminator or sunrise line gradually steal over the roughened surface, bringing new and striking craters into view each night. Around the time of quarter moon, or a little past, is one of the best times for telescopic views of the moon, because the huge craters Tycho and Copernicus are then in fine illumination. Close to the phase of full moon is never a good time, because there are no shadows on the rough surface then, and its entire structure seems to be quite flat and uninteresting, except for the streaks of rolls which radiate from Tycho in every direction, and are the only lunar features that are best seen near full. In a broad general way, the moon's surface, if compared with the Earth, differs in having no water. Our extensive oceans are replaced there by smooth, level plains, which were at first thought to be seas and so named. There are 10 or 12 of them all. Then we find mountain ranges, so numerous on the Earth, relatively few on the Moon. Those that exist are named in part for terrestrial mountain ranges, as the Alps, Caucasus, and the Apennines. But the nearly circular crater, a relatively rare formation on the Earth, is seen dotted all over the Moon in every size, from a fraction of a mile in diameter up to 60, 70, and extreme cases 100 miles. No mere description of plains or mountains and craters affords an adequate idea of the Moon's surface as it actually is. A telescopic view is necessary, or some of the modern photographs which give an even better notion of the Moon than any telescopic view. Many of the lunar craters are without doubt volcanic in origin. Others seem to be ruins of molten lakes. Many thousands of the smaller ones appear as if formed by violent pelting of the surface when semi-plastic, perhaps by enormous showers of meteoric matter. More than 30,000 craters cover the half of the lunar surface visible from the Earth, and hundreds of them are named for philosophers and astronomers. Measurement of the height of lunar mountains has been made in numerous instances, especially when their shadows fall on plains or surfaces that are nearly level, so that the length of the shadow can be measured. In general, the height of lunar peaks is greater than that of terrestrial peaks, owing probably to the lesser surface gravity on the Moon. About 40 lunar peaks are higher than Mont Blanc. Most astronomers regard it as certain that no changes ever take place on the Moon. Probably no very conspicuous changes ever do. Some, however, have made out a fair case for comparatively recent changes in surface detail. Extreme caution is necessary in drawing conclusions, because the varying changes of illumination from one phase to another are themselves sufficient to cause the appearance of change. At intervals of double illumination equal to 59 days, 1.5 hours, the terminator goes very nearly through the same objects, so that the circumstances of illumination are comparable. In Mare Serenitatis, the little crater named Linnaeus was announced to have disappeared about half a century ago. Subsequently, it became visible again, and other minor changes were reported, perhaps due to falling in of the walls of the crater. If one were to visit the Moon, he must needs take air and water along with him, as well as other sustenance. No atmosphere means no diffused light. We would see nothing unless the sun's direct rays were shining upon it. Anyone stepping into the shadow of a lunar crag would become wholly invisible. No sound, however loud, could be heard. Sound, in fact, would become impossible. A rock might roll down the wall of a lunar crater, but there would be no noise, though we should know what had happened by the tremor produced. So slight is gravity there that a good ball player might bat a baseball half a mile or more. Looking upward, all the stars would be appreciably brighter than here, and visible perpetually in the daytime as well as at night. If one were to go to the opposite side of the moon, he would lose sight of the Earth until he came back to the side which is always turned toward the Earth. Even then, the Earth would never rise and set at any given place, as the moon does to us, but would remain all the time at about the same height above the lunar horizon. The Earth would go through all the phases that the moon shows to us here. Full Earth occurring there when it is new moon here. Our globe would appear to be nearly 4 times broader than the moon seems to us. Its white polar caps of ice and snow, its dark oceans, and the vast cloud areas would be very conspicuous. Faint stars, the zodiacal light, and the fully solar corona would be visible, probably even close up to the sun's edge. But although his rays might shine upon the lunar rocks without intermission for a fortnight, probably they would still be too cold to touch with safety. On the side of the moon turned away from the sun, the temperature of the moon's surface would fall to that of space, or many 100 degrees below zero. Chapter 29. Eclipses of the Moon. Of all the weird happenings of the nighttime sky, eclipses of the moon are the most impressive. Rarely is there a year without one. What is the cause? Simply the Earth getting in between the sun and moon, and thereby shutting off the sunlight, which at all other times enables us to see the moon. As the Earth is a dark body, it must cast a black shadow on the side away from the sun, and it is the moon's passing into this shadow, or some part of it, that causes a lunar eclipse. Sun and Earth being so different in size, the Earth's shadow must stretch away from it into space, growing smaller and smaller until at length it comes to an end. The apex of a cone 857,000 miles long. If we cut off the shadow at the moon's distance from the Earth, we find it about 6,000 miles in diameter at that point, and this accounts for the fact that the curvature on the side of the moon, when the eclipse is coming on, and where it is dropping into the shadow, is always much less rapid than the curvature of the moon's own disk is. When an eclipse is approaching, the eastern limb will be duskily darkened for half an hour or more, because the moon must first pass through the outer penumbra, or half-shadow, which everywhere surrounds the true shadow itself. If the moon hits only the upper or lower parts of the shadow, the eclipse will be only partial, and during the progress of the eclipse it will seem as if the uneclipsed part had swung or twisted around in the sky, from the western limb of the moon to the eastern. But when the moon passes through the middle regions of the shadow, the eclipse is always total, and direct sunlight is wholly cut off from every part of the moon's face, for a greater or less length of time, according to the part of the shadow through which it passes. When passing centrally through the shadow, the total eclipse will last about 2 hours, as the moon's diameter is about 1/3 of the breadth of the shadow, and the eclipse will be partial about 2 hours longer, an hour at the beginning and an hour at the end, because the sun moves over her own breadth in about an hour. While the moon is wholly immersed in the shadow, her body is nevertheless visible, as a dull, tarnished copper disk, and this is caused by the reddish sunlight which grazes the earth all around, and is refracted or bent by our atmosphere into the shadow itself. If this belt or ring of terrestrial atmosphere happens to be everywhere filled with dense clouds, as was the case in 1886, Even the familiar copper moon of a total lunar eclipse disappears completely in the black sky. Quite different from a solar eclipse, all the phases of a lunar eclipse are visible at the same time on Earth, wherever the moon is above the horizon. Eclipses of the moon are therefore seen with great frequency, at any given place as compared with solar eclipses, which are restricted to relatively narrow areas of the Earth's surface. Nor are lunar eclipses of very much significance to the astronomer, mainly because of the slowness and indefiniteness of the phenomena. It is a good time to observe the occultations of faint stars at the moon's edge or limb, and several such programs have been carried out by cooperation of observatories in widely separate regions of the world. The object being improvement in our knowledge of the distance of the moon and in the accuracy of the mathematical tables of her motion. Search by photography for a possible satellite or moon of the moon has been made on several occasions, though without success. A lunar eclipse was first observed and photographed from an aeroplane, May 2nd, 1920. At the request of the writer, 2 aviators of the United States Navy ascended to a height of 15,000 feet above Rockaway and secured many advantages accruing from great elevation in viewing a celestial phenomenon of this character. And that's the end of a chapter, and the next one looks like a long and interesting one, so I'm going to call it there. This has actually come a little short, so I think I'm going to throw a little surprise on the end, so carry on listening if you're awake. And if you'd like to pick up where I'm leaving off, you can, as always, find the original of the book on Project Gutenberg at the link in the show notes. It's a new month, so we're going to a new poet, Helen Hunt Jackson. A Calendar of Sonnets, April. No days such honoured days as these, while yet fair Aphrodite reigned, men seeking wide for some fair thing which should forever abide. On earth her beauteous memory to set, in fitting frame that no age could forget. Her name in lovely April's name did hide, and leave it there, eternally allied. To all the fairest flowers spring did beget, and where fair Aphrodite passed from earth, her shrines forgotten, and her feasts of mirth. A holier symbol still in seal and sign, sweet April took, of kingdom most divine. When Christ ascended, in the time of birth, of spring and enemies, in Palestine. September. The goldenrod is yellow, the corn is turning brown, the trees and apple orchards with fruit are bending down. The gentian's bluest fringes are curling in the sun. In dusty pods the milkweed its hidden silk has spun. The sedges flaunt their harvest in every meadow nook, and asters by the brookside make asters in the brook. From dewy lanes at morning, from grape sweet odours rise. At noon the roads all flutter with yellow butterflies. By all these lovely tokens, September days are here, with summer's best of weather and autumn's best of cheer. But none of all this beauty which floods the earth and air is unto me the secret which makes September fair. 'Tis a thing which I remember, to name it thrills me yet. One day of 1 September I can never forget. Danger. With what a childish and short-sighted sense fear seeks for safety, reckons up the days of danger and escape, the hours and ways of death. It breathless flies the pestilence, it walls itself in towers of defence. By land, by sea, against the storm it lays down barriers, then comforted it says, this spot, this hour is safe. O vain pretence! Man born of man knows nothing when he goes. The winds blow where they list and will disclose to no man which brings safety, which brings risk. The mighty are brought low by many a thing too small to name. Beneath the daisy's disk lies hid the pebble for the fatal sling. For this month, we're looking at the work of Paul Laurence Dunbar. Summer in the South. The oriole sings in the greening grove, as if he were halfway waiting. The rosebuds peep from their hoods of green, timid and hesitating. The rain comes down in a torrent sweep, and the nights smell warm and piney. The garden thrives, but the tender shoots are yellow-green and tiny. Then a flash of sun on a waiting hill, streams laugh that erst were quiet. The sky smiles down with a dazzling blue, and the woods run mad with riot. We wear the mask. We wear the mask that grins and lies. It hides our cheeks and shades our eyes. The debt we pay to human guile, with torn and bleeding hearts we smile, and mouth with myriad subtleties. Why should the world be overwise in counting all our tears and sighs? Nay, let them only see us while we wear the mask. We smile, but O great Christ, our cries to thee from tortured souls arise. We sing, but oh, the clay is vile beneath our feet and long the mile. But let the world dream otherwise, we wear the mask. Life's tragedy. It may be misery not to sing at all, and to go silent through the brimming day. It may be misery never to be loved, but deeper griefs than these beset the way. To sing the perfect song, and by a half-tone lost the key, there the potent sorrow, there the grief, the pale sad staring of life's tragedy. To have come near to the perfect love, not the hot passion of untempered youth, but that which lies aside its vanity and gives for their trusting worship truth. This indeed is to be accursed. For if we mortals love, or if we sing, we count our joys not by what we have, but by what kept us from that perfect thing. A golden day. I found you and I lost you, all on a gleaming day. The day was filled with sunshine and the land was full of May. A golden bird was singing, its melody divine. I found you and I loved you and all the world was mine. I found you and I lost you, all on a golden day. But when I dream of you, dear, it is always brimming May. Morning. The mist has left the greening plain, the dewdrops shine like fairy rain. The coquette rose awakes again, her lovely self adorning. The wind is hiding in the trees, a sighing, soothing, laughing tease, till the rose says, "Kiss me please, 'tis morning, 'tis morning." With staff in hand and careless free, the wanderer fares right jauntily, for towns and houses are, thinks he, for scorning. My soul is swift upon the wing, and in its deeps the song I bring. Come love and we together sing, 'tis morning, 'tis morning. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. Good night, and sweet dreams.